artificial intelligence models operate as calculator. A query moves through the system's ecosystem of computational nodes. The primary cognitive core is decoupled into 4 specific, isolated components: an orchestration gateway, a cognitive sandbox, perceptual memory, and a strict verifier. By isolating these components, we can engineer physical laws and deterministic verification directly into the system's reasoning process. When an input arrives, the orchestration gateway acts as a traffic controller. It determines if a prompt requires a simple data search, or if it needs to be routed deep into the core for synthetic synthesis. Complex problems are sent to the cognitive sandbox. This is a secure computational workspace where the system can test ideas without affecting the final output. This diagram shows the internal validation loop. The system generates candidate solutions and deliberately attempts to break its logic. It builds temporary programs to run practical physics simulations. If a script fails, the system uses that feedback to immediately branch to a new strategy. The processor managing this workspace is the Large Quantitative Model, or LQM Perceptron. The LQM is an active meta-orchestrator. It observes the raw data, evaluates its own internal state, and assembles the necessary reasoning pathway on the fly. It autonomously selects the specific tools required for a task, scaling from basic linear algebra for simple cases up to complex differential fluid dynamics. By utilizing this self-play and simulation, the system generates its own pristine data, autonomously ironing out errors without any human intervention. This visual highlights the verifier, which utilizes neuro-symbolic integration. At the top of the funnel, the neuro phase uses neural networks to brainstorm creative solutions that lack deductive logic. At the bottom, the symbolic phase uses hard-coded solvers to mathematically call hallucinations. We can see this mechanic in practice within the field of cardiac diagnostics, specifically when identifying motion abnormalities in the heart wall. The system aligns a one-dimensional electrical command, the EKG trace, directly to the multi-dimensional kinematic execution of an echocardiogram video. Using the PyTorch code shown here, the architecture isolates microsecond markers in the electrical signal to create a precise temporal anchor for the video frames. Contrast this with traditional AI, where simple pixel matching often misinterprets image noise from patient obesity or equipment artifacts as a medical anomaly. The synthetic architecture's hydrodynamic sandbox flags that sluggish muscle wall as a causal violation of physics, mathematically rejecting the false positive. Grounding the output in hard biophysical constraints ensures the final solution is a proven physical reality, not a statistical guess. The final node is perceptual memory. Instead of storing information as flat text, this component uses dynamic, graph-based ontologies. During the materialization phase, when the system verifies a novel structural rule, it integrates that concept into its permanent library to build its long-term world logic. This cumulative memory changes product development from a building process into an evolutionary one. The role of the human engineer shifts. They no longer build geometries, they establish absolute mathematical boundary conditions, like maximum weight and temperature. The architecture then maps millions of structural variations across vast search spaces to produce counterintuitive, bioorganic blueprints. By exploring millions of variations simultaneously, the architecture identifies specific geometries that human engineers would typically overlook, resulting in components that outperform traditional hand-built designs. But this architectural leap creates a complication. It triggers a crisis of knowledge in scientific research. This diagram illustrates the nonlinear logic pathways and multidimensional processing occurring inside the framework. This is the black box epistemic crisis. The system consistently arrives at correct scientific conclusions, but it does so through logic structures that human minds cannot trace. This results in a unique advantage. The system can point to unorthodox research directions that human cognitive biases or historical assumptions would usually filter out. However, peer verification, the foundation of the scientific method, becomes difficult when humans cannot retrace the system's internal steps. Experts are forced to rely on successful outputs from a system whose internal decision-making processes they cannot fully decipher. For expert practitioners, this transition presents a risk of severe skill atrophy. Offloading the trial and error phases of research and hypothesis testing to an autonomous system risks degrading a scientist's own foundational intuition over time. There is also a broader societal risk, cognitive alienation. As these synthetic minds scale from deep science to civic design, we risk living in an environment engineered by an alien cognitive framework that defies human intuition. This makes our operational objective clear. We must ensure that fluid neural systems remain encased by deterministic symbolic frameworks. Human intent, represented here by the golden sphere, must remain central and structurally grounded to biophysical reality. The measure of synthetic intelligence will not be the elegance of its synthesized molecules, but our ability to integrate this architecture in a way that elevates human potential rather than overriding it.
I am absolutely thrilled to have you here today, because we're going to demystify
We're exploring how AI finally moves beyond just language, grasping actual physical reality.
Seriously, if LLMs basically just guess the next word, how do we build AI that understands physical laws?
Enter the LQM. It's an analytical engine bound by real-world thermodynamics, not just simple statistical patterns. Unlike standard AI that just predicts patterns, this new synthetic intelligence roots its entire logic in actual physics.
So on one side, you've got statistical guesswork. On the other, true, physics-grounded digital twins.
Notice how we completely shift away from human text, moving straight into first principles physical simulation.
Because honestly, traditional AI is essentially just a giant calculator trained on words. Zero physical grounding.
To stop hallucinations dead, LQMs use a mathematical funnel, aggressively culling any ideas defying the laws of physics.
They literally act like a firewall, testing hypotheses against mass conservation and strict thermodynamic forces. The secret sauce? Using ordinary differential equations to mathematically map out complex, real-world human physiology. This guarantees biological states only change via actual physical processes, no random statistical generation allowed.
But wait, how exactly do we model these continuous states using just sparse, occasional lab tests?
Continuous discrete Bayesian filtering bridges that exact gap. It mathematically predicts what physically happens between doctor visits. We feed it dense proxies, like smartwatches, tracking glucose and heart rate between those rare blood draws. Advanced particle filters crunch that wearable data, computing high-resolution biological states while quantifying all mathematical uncertainty.
Next, this robust LQM verification engine gets embedded directly into a live, clinical production environment.
Using JAX, we rapidly scale the whole shebang with GPU-accelerated ODE integration for thousands of patients. The final result? It isn't a statistical guess, it's a mathematically proven, physically simulated clinical reality.
Now, if the LQM disagrees with standard analytics by over 15%, it automatically flags it. We're going to be looking under the hood at the mechanics of the Large Quantitative Model, or LQM, Perceptron engine, and specifically focusing on its cluster feature engineering. If you've ever wondered how we can actually bridge the gap between artificial intelligence and the undeniable laws of physics and medicine, well, you are definitely in for a treat.
Before we get into all the heavy math and the system architecture, I want to pose a really high-stakes question to you. What happens when a medical AI is confidently wrong? Just imagine for a second the inherent danger of a clinical decision support system making a fluent, highly articulate, but completely scientifically invalid guess about a patient's health. The stakes literally couldn't be higher.
Right, so this is a phenomenon known as confident wrongness. We see this when generative algorithms produce clinical recommendations that are internally consistent, meaning, they sound perfectly logical to a human reader, but they completely violate basic biological reality. Relying on simple generative guesses in a clinical setting is just a massive risk. It requires a total paradigm shift. We need a system that doesn't just guess based on language patterns, but actually verifies its answers based on physical laws.
Okay, let's dive into this. Here is our game plan for today. We'll start with the high-stakes problem of AI hallucinations, look at the firewall solution, and then get into the really fascinating stuff: cluster feature engineering and physics-based digital twins. Finally, we'll cover the verification sandbox and architecting ironclad clinical trust.
Section 1. The high-stakes problem.
To really grasp the value of the LQM Perceptron, we absolutely have to recognize the critical need for an explicit,
auditable scientific consistency enforcer. This comparison perfectly illustrates the conceptual leap we're making here. On one side, you have the classical perceptron from the 1950s, raw numerical inputs, simple dot products, and a basic binary pass or fail. But the LQM engine completely changes the game. It evaluates structured scientific claims using actual physical equations and clinical guidelines, and it outputs a graded confidence of scientific consistency. We're moving away from simple guessing to evaluating true physiological plausibility.
Section 2. The firewall solution.
So how do we actually deploy this engine in a real-world architecture? We use it as the ultimate pre-output firewall. Acting as a scientific meta-orchestrator, it sits right between the AI's creative sandbox and the clinician. It functions as an active, perceiving agent that evaluates a patient's complexity and dynamically selects the math needed, scaling from basic linear algebra all the way to full differential fluid dynamics on the fly. This allows it to achieve what we call true concept formation. If it discovers a novel, successful combination, like linking an EKG metric to an acoustic frequency, it saves it. By demanding this intense level of coherence, it stops AI hallucinations dead in their tracks.
Section 3. Cluster feature engineering. Now let's look under the hood at the exhaustive, physics-inspired data architecture that powers this cognitive workspace. The LQM exploits incredibly high-resolution temporal data and nonlinear interactions across very specific categories. We're not just looking at a static lab result here. We're looking at derived time series, like the rate of change of a hormone over 6 months. We pull dynamic surrogates from continuous glucose monitors. We track circadian rhythms like core body temperature, and we even quantify patient-reported outcomes into hard, computable metrics. Now, what's really interesting is how these features come together to create a highly specific patient vector. Take this example of a patient with suspected polycystic ovary syndrome and a concurrent thyroid disorder. Instead of just a snapshot, the LQM is looking at the TSH 6-month slope, a specific temperature measure, an elevated LH to FSH ratio of 2.4, and a high hypothyroid symptom score. By engineering these specific, physics-inspired features, the LQM is capturing the complete mechanistic reality of the patient's endocrine system, not just statistical noise.
Section 4. Physics-based digital twins.
So, how does the LQM actually use those cluster features to build a mathematical, physiological replica of your body? It calculates latent hormonal states via deconvolution. I know, that is quite a mouthful, but the core concept is absolutely brilliant. In reality, your lab draws are sparse, maybe once every few months. But the LQM needs daily data to verify its analytics. So it uses state space models and physical conservation laws to infer the missing clues. It's essentially estimating your unmeasured free cortisol using dense, daily proxies from things like your smartwatch.
And here is the real kicker. Unlike purely statistical models, the LQM uses coupled ordinary differential equations to model true human biology. It literally encodes the laws of physics. It calculates mass and energy conservation during hormone binding, it uses chemical kinetics for rate processes, and it even models your hypothalamus-pituitary axes using feedback control theory. It's essentially treating your brain's glands like the nested PID controllers you'd find in an advanced engineering system. It's a true, functioning digital twin.
To handle the massive computational load of comparing those sparse lab visits against this complex model, the system uses continuous discrete Bayesian filters. Specifically, particle filters and ensemble common filters. Think of it like running a highly sophisticated weather forecast, but for your internal chemistry. This heavy lifting allows the LQM to accurately predict exactly what's happening in the unmeasured times between your doctor visits.
Section 5. The verification sandbox.
Let's move along and see how this physics-based modeling acts as the ultimate judge in an automated verification loop. First, the LQM builds highly accurate reference clusters using Bayesian models based on those rich features we just discussed. Meanwhile, the standard production AI runs a simpler, faster clustering to get hard labels. Step 3 is where the magic happens. The system compares the agreement between the simple AI and the deep LQM. It generates an aggregated confusion matrix to identify systematic errors, and ultimately, it triggers automated actions based on the mismatch rate.
And that brings us to a very specific, absolutely crucial number, 15%. If the disagreement rate between the fast production AI and the physics-based LQM exceeds this exact 15% threshold for a cohort of patients, the system automatically schedules a retraining of the production analytics. It explicitly flags the simple AI and says, hey, you are missing the true physiological phenotype here. Recalibrate. Finally, Section 6, Architecting Ironclad Clinical Trust.
This really brings our entire narrative home. I want to leave you with a thought directly from the source material. The output delivered to the physician is not a guess. It is a mathematically proven, physically simulated clinical reality. Just imagine a future where artificial intelligence in healthcare is universally bound by the undeniable laws of physics. If we can eradicate confident wrongness and literally test every recommendation in a cognitive workspace before a doctor ever even sees it, how many more lives could we save? That is the true power of the LQM Perceptron. Thank you so much for joining me. Keep questioning.
Must be prioritized.
But that ignores efficiency.
Efficiency of cost.
True